Modern graphics cards are marvels of engineering, integrating complex thermal and electrical systems tightly. The multi-layer PCB acts as the electrical backbone of the card. High-speed memory banks buffer gigabytes of critical texture data. The central silicon core handles massive parallel computation loads. Massive heat sinks and copper pipes manage intense thermal output. Zooming into the silicon reveals the streaming multiprocessor, the fundamental engine of modern graphics processing. Thousands of FP32 units handle standard floating point calculations. Specialized tensor cores accelerate matrix multiplication for AI workloads. The warp scheduler manages thread groups for maximum parallel efficiency. Low-latency shared memory keeps critical data close to compute units. High-resolution textures require massive storage capacity and wide pathways for rapid access. GDDR6X modules hold large texture files in local storage. The memory bus width acts as the highway's lane count. Wider buses feed the processor core without dangerous bottlenecks. Texture mapping units wrap 2D images onto 3D geometry to create lifelike surfaces. Vertices define the shape of the untextured polygon model. High-resolution 2D bitmaps provide surface detail and color data. The texture mapping unit maps coordinate data to surface pixels. Filtering algorithms sharpen textures at oblique viewing angles. The final output is a realistically skinned 3D object. Consumer cards prioritize high clock speeds and specialized hardware for real-time rendering performance. High-velocity fans maintain thermal headroom for sustained boost clocks. GDDR6X memory provides high-speed texture buffering for 4K gaming. Modern DisplayPorts support high refresh rates and variable sync. Workstation cards prioritize data integrity and certified stability for critical professional workflows. The blower design ensures consistent airflow in multi-card server racks. Error-correcting memory prevents single-bit errors during long render computations. Optimized silicon delivers sustained performance for certified CAD applications. Multiple, high-resolution outputs support complex multi-monitor visualization setups. The H100 SXM module redefines performance with massive scalability for deep learning workloads. The central 80 billion transistor die powers massive transformer acceleration. 6 HBM3 stacks provide over 3 terabytes per second of bandwidth. Mezzanine connectors enable ultra-fast NVLink communication between multiple GPUs. Cooling solutions vary dramatically between consumer gaming cards and high-density data center hardware. Open-air designs prioritize maximum airflow for individual desktop environments. Blower coolers channel heat directly out through the chassis rear. Passive heat sinks rely entirely on high-velocity server rack airflow. High-speed interconnects define the scalability limits of modern multi-GPU systems. Standard PCIe lanes often create bottlenecks during massive data transfers. NVLink bridges bypass the CPU for direct high-bandwidth GPU-to-GPU communication. This architecture enables terabytes of throughput essential for training large models. We align these distinct architectures with their specific deployment requirements. Consumer cards prioritize high clock speeds for real-time rendering. AI accelerators utilize massive memory bandwidth for parallel training. Embedded units balance performance per watt for autonomous devices. This framework identifies the optimal hardware for your workload.